Hopefully we now have some understanding of how to deal with both the solvent and the solute in a dilute solution, especially when the solute is non-volatile. But what we haven't answered yet is exactly how do we determine the activities of those non-volatile solutes. They're going to be very difficult to measure because measuring the very small vapor pressure of a non-volatile substance, especially when it's very dilute in a solution, I'll just say it would be extremely difficult experimentally. It turns out, though, that there's a way that we can do that, or the way we can evaluate that activity by making measurements on the solvent itself. So let's once again start with our standard expressions for the chemical potentials. This is the actual chemical potential, I should say the accurate one. However, in the ideal limit, the activity goes as the mole fraction. Now what I want to do is I want to manipulate these equations a little bit so that we can get to some good relationships or some interesting relationships. Now what I'm going to do is I'm going to subtract mu j solution from both sides of both of these equations and then move the RT log of something over to the other side. So in other words, I'll have a solution that looks like this. I'll have negative RT log of the activity is equal to the difference between the pure substance chemical potential and its solution chemical potential. All right, now I'm going to do this for both the solvent, which is component 1, so let me change these J's to 1s, and the solute, which is component 2, but I want to focus on the solution. I want to focus on the solvent first because that's the thing that we're going to be using to measure these activities. Now, if I did the same kind of manipulation for this second equation as I've done here, I would end up with minus RT log of x1 is equal to mu1 star minus mu1 solution. Okay, but this is in the ideal limit, so I want to make sure that I'm continuing to do that. So that means that really this is only going to be good in that limit as the mole fraction is going to 1. When we're not in that limit, this quantity is not going to equal the difference in those chemical potentials. It's going to equal something else. And that something else might give us a way to measure, if you will, the degree of non-ideality in this solution. So now what I'm going to do is if I took the ratio of this side to this, so I'll have mu sub 1 star minus mu1 solution over RT log of A1, okay, I should get 1. Okay, that's the actual and accurate answer. If I do the same for the second equation, I would have mu1 star minus mu1 of solution divided by RT log of the mole fraction. Now in this case I said I'm not going to get 1 because these are not really actually equal to each other. So I'm just going to assign this to be some number which I'll call phi. Now it turns out this number has a name, don't they all? This one is called the Osmotic Coefficient. And in fact, it is a measure of non-ideality. That is to say, the degree to which it doesn't equal 1 will tell us just how non-ideal a solution would be. All right, so if I want to get a handle on this and I don't want to be evaluating chemical potentials, one of the things I can do is take the ratio of these two expressions. So I'll take this one and divide by this one. Now you'll notice that the numerator is the same in both of these cases, so that's going to cancel. And what I'll end up with is an expression that and also, by the way, the RTs are going to cancel. What I'll end up with is a really tidy expression that looks like this. Log of the activity divided by log of the mole fraction is just equal to my osmotic coefficient. So this is going to be the means that we'll use to evaluate that osmotic coefficient in some ways, or the way we'll use the osmotic coefficient, I should say, to actually get a handle on how to connect the activities of the solvent with the solute. Now let's see how does that work. Now first of all, I'm going to unpack this one a little bit and write this as log of the activity is just the osmotic coefficient times the log of the mole fraction. Now, when I have a dilute solution, as we're basically projecting here, this means that so dilute solution means that x2 is going to 0. Okay, we're having a very low mole fraction in the solute. So that means that, in fact, I can do a very handy manipulation of logarithms and say that the log of the majority component, the solvent, can be rewritten as log of 1 minus the solute, but this is a really small number. And there is a special property of logs that says that when x2 is really small, that this is approximately equal to negative x2. You should try that out on your calculator. Try doing the log of 1 minus 0.01. So that's log of 0.99. You should get that it's about equal to negative 0.01. Okay, but this particular property is very handy, and it allows us to directly substitute the mole fraction of our dilute component for the log of the mole fraction of the majority component. And so we're going to take advantage of that. And it means that I can rewrite this equation here as log of A1 is equal to negative x2 times this osmotic coefficient. Now I'm going to go another further step. Last time we talked about, instead of using mole fractions, using the concentration in molality. And so that I'm going to make that change. So that means that I can express this mole fraction as the molality divided by, and if we're in water, let's assume we're in water, it'll be 55.508 plus molality. But this molality is going to be so small that I can effectively ignore it. Okay, it's going to be small in comparison to this. So that means that when I have this expression, I can rewrite this as 55.508, or in other words, the effective number of moles of my solvent times log of the activity of the solvent is equal to the molality of the solute times this osmotic coefficient. All right, so this is how we're going to try and make our way from measuring something that's relevant for A1 to tell us something about A2. All right, now the way that we normally will do something like this is by using the Gibbs-Duhem equation. So let me remind you that the Gibbs-Duhem equation, in its form that we originally saw it, involved the chemical potential, and so it was something like the number of moles of component 1 times the change in the chemical potential of that component plus the number of moles of component 2 times the change in the chemical potential of that component is equal to 0. But we've seen that we can rewrite this in terms of the activities because the log of the activity is akin to the differential of that is akin to the differential of the chemical potential. So in fact, one can rewrite this equation in a much more helpful form as N1 d log A1 plus N2 d log A2 is equal to 0. So this is just an alternative form of the Gibbs-Duhem equation, but written in terms of activities. And we already have a good handle on where we're going to go with that because we have this relationship here and actually this relationship here. Now notice that we already have N1 times log of A1, so this thing here is going to turn into 55.508 times the derivative or differential of log of A1. Okay, right here. What about this thing? Well, this is going to be the effective number of moles, which is given by the molality in this case. So it'll be the molality times the times the differential of the log of A2. Okay, this is the thing that we're after. Okay, this is what we're trying to measure from this, but we want to use information about the solvent to get that. Now, this thing here, we have already seen we can effectively write it like this. So, or I should say really like this. So in effect what we have is, since 55.508 is equal times log of A1 is equal to this, that means this whole thing here is going to be the differential of this. So negative d of m phi over here. And this is all equal to 0. So now when I rearrange this equation, I'm going to end up with a net equation that looks something like the differential of the log of A2 is equal to 1 over m times, I'm sorry, and that negative turned into a plus, times the differential of m phi. And so this is going to be the equation that we want to solve. Now, I'm not going to take you through the details of that. I will say, though, that we want to rewrite A2 in terms of its molality and its activity coefficient. So this is going to be the activity coefficient written in terms of molality. So you may want to go back and take a look at the table at the end of the previous video that talks about this equivalence, this definition for the activity coefficient. But when we substitute this in for A2 over here, and we work out this total differential of the product, and then integrate from basically a molality of 0 to some undetermined molality, we can write down the final result for the log of the activity coefficient, and it will be given by, and this is, I should always specify that this is for molality, it will be given by this quantity, the osmotic coefficient minus 1 plus the integral of this actually fairly simple looking integrand of the osmotic coefficient minus 1 over m, the concentration. And this is just an integration variable for the variable that ranges from 0 molality to some non-zero molality. All right, so what we have here is essentially a prescription for determining the activity coefficient for the dilute solute, that's this, in terms of quantities that we can obtain by measuring the solvent. How does this work? All right, so here's the process that one might follow. Okay, we're going to set up a solution, okay, with a concentration of m molality. Okay, for that solution, I'm going to determine first what is the activity of the solvent. Okay, so that activity, and remember that activity is just the ratio of its vapor pressure to its pure vapor pressure. Well, we can measure the vapor pressure of the solvent because there's a lot of it there, and it's easy to measure, it's volatile. And we presumably will know the vapor pressure of the pure solvent, so we can always divide that. So we can determine the activity of the solvent for any concentration, but in particular even dilute concentrations. All right, and for each of these, we'll also determine what the mole fraction is for the solute, knowing its concentration, and it will simply be roughly, and I'll make this an approximately, m over 55.508. Okay, we're just using this expression up here. All right, so once we have both of those, now we can evaluate the osmotic coefficient. Okay, the osmotic coefficient, remember, was simply the log of the activity over the log of its mole fraction, but we can also write that as the log of the activity of the solvent divided by the mole fraction of the solute with a negative sign, because remember it was equal to, where is it up here? It's equal to negative AX2 over here. All right, so we've evaluated the activity of the solvent, we've evaluated the osmotic coefficient. So we have essentially what we need in this formula to get the activity coefficient for the solute, but we're going to need to measure this repeat for several different concentrations, because what we're going to want to do is eventually get some estimation of how this osmotic coefficient varies with the molality. Okay, and once we have that, then we can numerically integrate this expression, to obtain the activity coefficient for the solute. All right, so once we've obtained that activity coefficient, then we can find A2 is just equal to the molality times the activity coefficient of the solute. So the amazing thing about all of this is that we've basically made a measurement on our solvent, which is in a great majority, and use that measurement to determine the activity of the solute, which is not only in a great minority in this mixture, but it's not very volatile. So it's not something that we can easily measure on its own. All right, so it shows you a way that we can use the Gibbs-Duhem equation to connect two quantities and measure something useful, even though it's difficult to measure.